Okay, I think I started.
Okay.
So good morning, good afternoon, good evening, everyone, since I don't know which time zone you are. Today we'll have our Texas A&M ARMA R&D series, and we are featuring Mr. Babak Heidari. Babak Heidari is an experienced geoscientist and petroleum engineer with an extensive knowledge, more than 15 years in oil and gas industries in several locations, Middle East, East Asia, and North America. His professional career involved several roles and responsibilities in geomechanics, drilling, and petrophysics consulting, and research such as business development, sales and marketing, and team project management and leadership. And with that, Mr. Heidari, it's all yours.
And thank you very much, Serhi, for the introduction. Good morning, good afternoon, and good evening, everyone. Appreciate joining the talk, and I hope that I'll be able to pass the message around this very important topic that I found very fundamental and critical in geomechanic, in geomechanic, geotechnic, and geothermal business and petroleum engineering business. So please keep in mind that this presentation, it was prepared with the mindset to be just educational use only, and then through, I know that some slides going to appear to some of you basic, and maybe you have the knowledge already, but I appreciate your patience through those slides as I'm trying to make the ground ready for the large group of audiences here, and which mostly are going to be the university students. So let's dive in. Okay, I start my presentation by providing an overview of the topic and some introduction that what are the Farfield stresses and why they are critical. Then I will further elaborate on the techniques to measure Earth's in situ stresses and how to estimate them. And then the discussion will continue around what is the relation between the borehole, around the borehole stresses and Farfield stresses, and why. Sorry. Okay, I would appreciate that if you mute your microphone through the call, through the presentation, and I'm going to be available after the presentation to answer your question if there is any. Thank you. So I will continue to elaborate further about this, as I mentioned, relation between the borehole stresses and Farfield stresses, and why, in my view, it is the best technique to come up with the Farfield stresses. And then through the presentation, I will explain what are the advantages and disadvantages of each approach and what are the challenges. And at the end, we're going to have a Q&A session, and I'm trying to hear from you and hopefully answer your questions. So basically, there are lots of operations in the oil and gas, geothermal, and geotechnical industries that are highly relying on the Farfield stress information. For example, if you want to make a drilling, if you want to drill a borehole, defining a safe mud window and reaching to the target, and then optimizing the trajectory, they are all we need to have a mechanical earth model. And this mechanical earth model need Farfield stress as a main component. So if you are doing, for example, defining the completion tools and completion devices. So you need to come up and completion a strategy. You need to have a good understanding of the Farfield stresses. A stimulation, for example, if you want to do hydraulic fracturing, you know that defining the zone that you want to do the hydraulic fracturing and optimizing the pressure, and then optimizing So how much going to be the width and the length of the frag? All of these information need all of this calculation and consideration. They need Farfield stress as input. Production. So why still after production? So we reach to the target, we are producing from the field. Why still we need Farfield stress information? Because through the production, stress is going to change. So we are going to have stress alteration due to reducing the fluid from the pore spaces. And that stress alteration going to cause so many, it can cause so many difficulties. For example, fault reactivation, casing collapse, and compaction subsidence, for example. And these all, to address those issues and to prevent those issues, we need to have good understanding of Farfield stresses. And why I'm parking EOR and geothermal in one category? Because to my knowledge, they are pretty much close. And then I could park CCS also on this category, because the knowledge that we grasp on the EOR technology in the petroleum geomechanics, they are going to be relevant to geothermal and CCS as well. So in the EOR, we are injecting fluid. In the geothermal, also we are injecting fluid, cold fluid, and we are receiving hot fluid, or for example, steam. In EOR, pretty much the concept is that that temperature alteration is into the rock, into the formation, going to be pretty much same. CCS, there are also geochemical component to this geochemical alteration into this category of operations. So, but basically I can say that they are pretty much close. And then at the end of the operation, so we want to we want to abandon a field or abandon a well. So you need to make sure that the plug, for example, a cement plug that you are putting in place, going to stay safe and stable for a long time, for example, for a decade, or for example, cap rock is not going to be leaked through the reservoir repressurization. Okay. So right now, I just tried to give an overview of why Farfield stress information and knowledge about this is very critical. So now I'm going to discuss what are the Farfield stress components and what is the ERS model. So you heard about the mechanical ERS model, and you heard about the GEM, MEM, and it appears a bit complicated stuff. And to be honest, it is. So it has lots of components. It is like a big puzzle, and it has lots of components. It has easy pieces that you can place them in the corners easily. For example, there are, for example, young elastic properties, rock properties, overburden stress, and then pore pressure. They are not that complicated. They are still complicated. You have to do calculation. You need to have a proper strategy to define them. But the most complex one is Farfield stresses and minimum and maximum horizontal stresses, in my view, because they are the knowledge around this Farfield stresses, they are highly dependent on the other components of mechanical ERS model. And this is why mechanical ERS model basically, I forgot to mention, it is, we are trying to make a best representation of formation in regard to elastic, rock strength properties, and stress profile and pore pressure profile. And you cannot force one piece in the other piece location Otherwise, the final product going to look ugly and it's not going to be well representative of your formation, and it's not going to be basically useful. So you need to be very careful to define the mechanical earth model, which can be 1D or 3D. So I'm going to give an overview of the 1D mechanical earth model construction. So the 3D going to be more complicated, but every 3D model, they need 1D as a basis and foundations, okay? So how we can come up with the 1D mechanical earth model? So we need so many inputs. We need open hole log data, resistivity, sonic, image log, pore pressure information, surface map, seismic information, end of a report, DDR, daily drilling report, and daily geological report. To come up with and then we need to do data gathering and doing a review of the data and doing some candidate well selection, okay? As we came up with those candidate wells, so we need to establish mechanical earth model and those components of mechanical earth model. Every time we start with generating elastic and rocket strength profile. So which can be done based on for example, compressional sonic, shear sonic, density data. We start from dynamic. I'm not going through the steps to generate the 1D MEM. I have another purpose here, okay? So, and then we need to establish mechanical stratigraphy, which defines that what are the formations that we are dealing and we are facing, because different formations, they are going to behave differently, okay? Sorry. Okay, then we need to we can proceed to generating overburden stress and pore pressure profile. And they are pretty much related to each other. And I will explain that why overburden and pore pressure, they are related, and what is the relation of the pore pressure to the horizontal stresses. And at the last step, I can say that history matching is last step or fine tuning the model. But this is the last component of mechanical earth model. We are generating horizontal stresses, minimum and maximum horizontal stresses, direction and magnitude. And this is why this step is important, because it is relying on those steps that we took prior to generating the horizontal stresses. And horizontal stress is highly dependent on the other parameters. Okay. So, but what are the Farfield stresses? What are the components of the stress tensors in the earth and in the ground? So, whenever there is a rock or sediment underground, they are subjected to the stresses, which are, we call them principal stresses, and there are it has three components. Overburden or vertical stress, minimum and maximum horizontal stress, and they are perpendicular to each other. So you may argue that they are not always horizontal. That's correct. So they can be rotation around each of the components of the stress tensors, especially if there is a complex geological feature, for example, if there is a fault or if it is for example, fractures. So there could be a rotation if the geological formation in geology is in regard to geology is complex. So there could be a relation, there could be a rotation into these components of a stress tensor. But for simplicity, let's imagine that overburden is vertical and we have two horizontal stresses. So I'm not saying that they are different, but they are different in magnitude, but in general, we have two horizontal stresses. So these are the components of horizontal. This is overburden, minimum and maximum horizontal stress. And the easiest component of this stress tensor is overburden stress. And how to define this overburden stress? is by integrating the density data, integrating all the, for example, rock and fluid, and even considering the air gap to come up with the gradient of the density. And as we manage to define the gradient of the density, so this is the density log, and it is possible that in some intervals we don't have the density data, and this is how they came up with some techniques to extrapolate the density to the surface, because we need the composite density log from surface to TD to be able to run this integral equation, right? And then we can define the overburden gradient in SG or PPG, or I'm more familiar with these two units. I better to stick to these things. SG or PPG, and then we can define the pore pressure stress in the stress or pressure domain in the PSI or megapascal, for example. So overburden stress is easy. So it is one of the easy piece of that big puzzle. So we have, in general, we have a good control on the overburden stress. So let me give you a broad view of what it could be if you have heard about the different stress regime, for example, normal, thrust faulting, and struck and sleep, what they are. So we define the overburden stress, but depending on the order of the magnitude between the horizontal stresses and overburden, we can have three scenarios. So three stress regimes. So the simplest one is the normal, which is happening in the most of the formations and geographies. And then we can have thrust faulting and also a struck and sleep regime faulting. And where is the best place to learn about these things is by looking at the world stress map. This is the address to world stress map. So you can look at this link, and then you can also download this plot. And the good thing is that you can even have access. You have even access to the ASCII data. You can take this data and use it in your application. As of my knowledge, they are free. These data are free and open source. So I haven't seen any places that are asking for some payment for grabbing this data, and I was using for delivering project as well. And the good thing is that it is very interesting map. So you can understand what are in each location in the world, for example. So some places there are not much of data because some governments, they are not sharing data and they have restriction about the sharing the information. But most of the places that I have worked, so you can grab a good data basically. And they are saying that, for example, what is the source of this information? Some of them are based on the borehole data, some of them are based on the focal mechanism information, earthquake data, and some of them image log, mini frag. It has a legend to explain that what is the source of this information. And the color is defining what is the stress regime: normal, struck and sleep, and thrust faulting. Different color codes. It is very, very good to learn what is happening around your, for example, around your field, around your city that you are living, and you can correlate it with the earthquake and mountains chain, for example, to have overview of tectonic in your region. Okay, let me move to pore pressure. So you may ask that why I'm bringing pore pressure to this topic. and the reason is that I know that there is a strong relationship between the pore pressure and horizontal stresses. And by changing to the pore pressure, horizontal stress is going to change. And this is why I decided to give a quick overview of what is the pore pressure and what defines the overpressure, underpressure here. So basically, pore pressure is the fluid pressure in the void space between the grains of the rock, okay? And that pressure could be over, under, or hydrostatic. If it is hydrostatic, it's a hydrostatic column of the fluid. The fluid can be water or oil, any fluid basically. If the fluid pressure is hydrostatic, we can call it, we call the pore pressure at the depths of interest, we call it normal. And if the pore pressure goes higher than normal pore pressure or hydrostatic pressure, we are facing the overpressure situation. And if there is a depletion, for example, the pressure drops below the hydrostatic pressure, we are facing underpressure situation, okay? So hydrostatic pressure and under pressure zone, they're more or less easy to define, right? So it is same as rho g h. So you define the density of the fluid, and then you can come up with the pressure of the fluid, and then you can define the gradient. And the complication is around the overpressure zone. We can have two types of overpressure, type 1 and type 2. And basically they define that based on the dependency of the overpressure to the porosity. If the overpressure is related to porosity, and for example, if there is a rapid sedimentation, thick shale and low permeability, high compressible rock, and basically this is the situation, they call it under compaction correlates to overpressure. But on the other hand, if there is no relation with porosity, for example, shale uplift, source of fluid. So whenever I reach to this line, it reminds me a good story. So I was working in East Asia, and I had to calibrate my model based on some direct pore pressure information. And then I had a very hard time to calibrate my model. I was not getting a good match. And I was saying that, okay, I will explain that what's the compaction trend line and the normal compaction trend line. But I was forcing my model. I was trying to force my model to match to that direct pore pressure data. And later I found that they were injecting into that permeable sand zone. And the problem was that they didn't share this information with me right before proceeding to the study. And it was becoming misleading source of information, that direct pore pressure data for my model validation and calibration. So, and if there is no proper channel that the fluid pressure can escape. So these are the different, if there is a trap, for example, and these are the situations that the overpressure is not related to porosity. So, but I go slightly back. So I want to explain that, okay, if these are the pore pressures, how to define them, how to estimate or measure them. And then I will explain again that why this under compaction, how to use it in this broad view. So if we have, if you want to have direct measurements, so if we are facing with the permeable formation, for example, sand, we can use quartz gauge or pressure transducer equipment, such as MDT or XPT, so to come up with the direct pore pressure in the sand. If it is shale, still it is possible to get the direct measurement of the shale pore pressure. It is I have seen, if I remember correctly, it was shell that they tried and to get the direct pore pressure of the shell, and it took a very long time. It is not efficient process, but however, it's doable. It takes very long time because shell is has very low permeability. But what about the indirect or estimation of the pore pressure if we cannot measure it? So if it is sand, for example, if there is an influx or kick, we can use this information to calibrate our model. For example, if you know your mud weight, your depths, and then if you are seeing any kick, so you can back calculate that how much could be the pore pressure in your permeable zone or permeable interval. Then this is becoming very interesting that if it is shale, so in the impermeable formation like a shale, how to estimate pore pressure? And you may question that why it is even important, because shale is low permeability, is not going to kick. It is due to the fact that at the early days of the drilling, so even right now, so drillers, they don't like to get surprised. So they are trying to not act, I'm not saying that they like to act conservative, but they're running very serious operation, and it is very prone to risk and failure. So they want to be very careful. And they urged geologists and whoever has earth science knowledge to come up with some prediction of the pore pressure. And they were seeing that, for example, if they are going through the shale, after the shale, so there is overpressure, and they wanted to correlate this thing. So then so many people tried to come up with the methodology to define the overpressure due to this, as, for example, the sand layer is just below the shale and thick shale layer, for example. So if you heard about Eton, Bowers, so it is around the same topic. So they are saying that if there are measurements that they are sensitive to porosity, such as resistivity, compressional sonic, even ROP, so which is related to porosity. If the porosity of the formation is high, so the ROP is going to be higher. So it's not as much sensitive and detailed as the borehole measurement, because it's the resolution and the way that they measure the ROP is not very detailed. But there is a correlation, there is a relation. So they try to establish the normal compaction trend line, and then whenever there is a deviation from normal compaction trend line, they translated that deviation to overpressure. This is what you are seeing here. So up to here, this is the top of the overpressure, and here the resistivity measurement is deviating from the established normal compaction trend line. This is the simplest way to present this one. So it is not, there are equations involved, and nothing is just to define the normal compaction trend line in the mechanical earth model toolbox and packages. So they are just defining normal compaction. The rest is going to be done by the software and the calculations behind. So this is basically around this overpressure, how to estimate it. And then I'm going to talk about the horizontal stresses and how to determine the horizontal stresses. So if there is no tectonic in your field or your reservoir, so we can say that the horizontal stresses are same. Let's imagine that we have a cylinder, empty cylinder, and we are pouring sand into the cylinder. And then we could imagine that at the bottom of this cylinder, So the stress is going to be same in any direction. And this is the situation, they call it uniaxial strain model. Here I'm just showing the maximum horizontal stress, but minimum horizontal stress is going to be same. And there is a simple relation of based on this equation. You need just overburden. This is effective overburden, this is effective horizontal stress. You need Poisson ratio and overburden to calculate the magnitude of the horizontal stresses. But in the petroleum geomechanic world, there is always tectonic. There is always a stress and isotropy, and we need to. The oil is located in not easy places. So, and there is always some complication to reach to the reservoir and bypass so many and pass through so many difficult formations, such as shales, such as formations which are overpressure, and there is always tectonic. You can use geological features. For example, if you are seeing this anticline, so by looking at this anticline, you may guess that this should be the direction of the maximum stress, right? And then there are other sources of information. So this is based on the focal mechanism, technique, and the earthquake information. This information, you can find them in the world stress map. And they are giving some idea about the magnitude of the stress, what is the stress regime, what could be the stress direction, but better not to rely on these geological features. They can give you a big picture, but they can be also, on the other hand, they can be misleading because they may not represent the current state of the stress in your field. So they could be coming from this could be the stress state at your field long time ago, million years ago. And maybe your field right now, at the initial, it was on the thrust faulting stress regime. Right now, it's acting in the normal stress regime. So the best way to grab the current state stress data on your field is looking at the borehole data. The good thing is there is a relation between the Farfield stresses and borehole, around the borehole stresses. And this is well explained in so many literatures. The basic one was established by Kirsch, and basically his equations are saying that if the formation is isotropic, homogeneous, you are going to have, he defined that how to back calculate the three components of stresses around the borehole. We call them hoop stresses. Hoop stress has three components. Hoop stresses has three components: tangential, radial, and axial. This is radial, tangential, and axial is along the borehole. So this is a top view. So this is a good thing. Since we are drilling a borehole, we are disturbing the formation, and then redistribution of the stresses inside the borehole going to project themselves in three other stresses. And if these three stresses are going to show some features, for example, breakout and induced fracture that I'm going to explain, so you can have a better current state information about your field stresses. So there are two components that you need to define to characterize your horizontal stresses: magnitude of the horizontal stresses and direction. So let's start by direction, which is a more simple one. So a structural geology and focal mechanism, as I explained, such as earthquake, they can give you a big picture of the stress direction, but we are not going to rely on them very much unless you don't have another data. Wellbore data, as I explained, if we are drilling a borehole, we are disturbing around the borehole stresses, and we are going to, depending on the pressure inside the borehole, we may face two types of failures. So one of them is shear failure, the other one is tensile failure. Shear failure, it is not simple breakout. So the breakout that we are saying breakout is a wide breakout. There are other type of shear failure happening around the borehole. But for the simplicity here, let's focus on the breakout. Breakout is shear failure, and it's happening in the direction of the minimum horizontal stress, which is the maximum stress concentration around the borehole. And tensile failure or induced fracture is happening in the direction of the maximum horizontal stress. So if we can observe, we can see these features by any tool inside the borehole, we can say that what could be the direction, and we should have those tools properly oriented and be able to measure their orientation. So we should be able to we should be able to understand what are the stresses direction. So one good source of this information are image logs. So there are different image logs. So there are resistivity. This is the full borehole. This is ultrasonic caliper. So, and this is most probably is the FMI caliper. This is a resistivity. This is ultrasonic. This is full coverage. This one doesn't have full coverage. So it is close to 360. This is the image log. So this is the projection of the borehole based on the resistivity or sonic measurements. And this is what feature that you are seeing here is breakout. And if it is properly oriented, so for example, here is between southeast, northwest, so you can get an idea about what could be the direction of the minimum horizontal stress, which is in this direction now. You can use oriented calipers, multi-arm caliper data, but you need to be very careful because you cannot, even these features can be misleading if you don't know properly what is the source of this information. Because key seats, borehole washouts, so they look similar, but they are not source of tectonic, and they are not source of the stress disturbance around the borehole. So this is based on my paper published back in 2017. And basically what I was doing, I was screening just the interval that was useful for this sort of algorithm and workflow. And the rest were just pure washout, for example. And then this interval, I picked this interval, and then based on this interval, this is the maximum horizontal stress direction. This is minimum one, this is the maximum. I defined it in this direction. And the other good source of the information is using the dipole sonic data. Because dipole sonic has a unique feature, it can get polarized based on the anisotropy. And here we are talking about the stress anisotropy, right? If the dipole sonic measurement can get polarized to, we call them fast and slow, and they are traveling in the different direction. And whenever there is a maximum stress concentration around the borehole, so fast shear is traveling, and in the direction of the, whenever there is a less stress concentration, minimum horizontal stress, minimum slow shear is propagating. Sorry for that. So I have another slide on the dipole sonic application, and I will elaborate further. An instrumented packer. So this is something that I'm currently busy at Integrity Insitu at the company that I'm working. So why I'm highlighting these two techniques? Because they are not relying on the borehole features. So as I explained, the image logs, caliper data, they can be misleading as well if they are not properly picked. So I can show you the induced shear failure, which is identical to the breakout. So the tensile failure, which is identical to the shear failure. And it's not easy to pick. So you should have another information to put together to decode this thing. So what about, I can say that the direction is quite easy. So the hard one is the magnitude of the horizontal stress. So you can use the friction model, Moore column friction model, just to define the boundaries. So basically saying that this fault or fracture, it was not a slipping, and then it was a stable, and how much could be the magnitude of the minimum and maximum horizontal stress based on the simple Moore column and defining the failure line. This is just pure boundary. But if you go more advanced, I explained that uniaxial strain model is the simplest form of the calculating the horizontal stresses based on the overburden and Poisson ratio can be used. And the complex one is based on the proelastic equation. This is popular. This is what I'm using in my whenever I'm doing consulting project or whenever I need to calculate the horizontal stresses, I'm using this equation. And this equation, this is the minimum horizontal stress equation based on the proelasticity concept. It has several components, Poisson ratio. This looks identical to the plane strain model, right? But it has other components. So pore pressure is coming to play, Biot coefficient, which is the contribution of the pore pressure into the effective stress, and then Poisson ratio is here, Young modulus is here, and there are two important components. These are EX and EY. These are the horizontal strain parameters. So in the direction of the maximum and minimum horizontal stress in the direction of the X and Y. So, and some people I know that they don't like this equation because they are saying so many parameters are involved. But this is one of the equations that you can come up with the continuous profile of minimum horizontal stress, and there is the same equation for the maximum horizontal stress, and you can come up with another curve for the maximum horizontal stress. So here I'm not going to talk about how to define how to generate the mechanical errors model. I'm just focusing on one component. But yeah, it has lots of components, but it is showing that the horizontal stresses are sensitive to the rock properties, which should be, right? So horizontal stress are sensitive to rock properties. If the rock properties changes, the horizontal stress magnitude should change. So this is the physics, simple physics around the rock mechanics. So there are other techniques that you can use to calibrate your model, because this is just, you can use it for the certain interval. So using the borehole breakout widths that some geomechanical engineers using to calibrate, I can use it as an indication of the model validation, for validating my model, but I'm not using this technique to back calculate the maximum horizontal stress magnitude. So basically this technique is saying that, okay, how much is the width of the breakout? And there is a relation between this width of breakout and the magnitude of the minimum and maximum horizontal stress. That's true, there is. But what is the problem with this technique is that, so breakout widths and the failure around the borehole is a time dependent. And if that failure is progressing, so And if there are drilling activities that are making this breakout become bigger in size and width, and you use this source of information to calibrate your model, most of the time, you're ended up overestimating your magnitude of your horizontal stresses. Or this is for maximum horizontal stress. And for the minimum, so whoever sticks to this methodology, they are using the mini-frag, and then for the calibrating. And I'm using mini-frag for the calibrating data as well. But this is the problem around this technique that I need to highlight. But I may use it for the calibrating my model as well. So another good source of information for the calibrating your model is mini-frag, LOT, extended leak-off test, which in my view, and whoever is involved in the geomechanic business and geomechanic consulting business, so we believe that the extended leak-off test is the best test, because we are going through 2 cycles at least, and then we are fracking the formation, and we are letting the formation to close and then reopening again. So to remove the effect of, for example, tensile strength of the rock, and so get a smoother measurements for the fracture closure pressure, which we are saying that this is equivalent to the minimum horizontal stress, basically. And by having this information, so if there is a breakdown that inducing a fracture, so we can use this information, breakdown pressure, pore pressure, and the minimum, if we have the minimum horizontal stress from the fracture closure pressure. So, and then by having the tensile strength information, which is the difference between the first fracture initiation and then reopening pressure. So you can get an idea about the tensile strength, and having the pore pressure and the bulk modulus of the rock. So you should be able to back calculate the amount of maximum horizontal stress. And then you can use dipole and instrumented packer intent. For example, the packer which has the calipers behind the packer. So I'm going to highlight, how much time do we have? So I'm missing the time, I guess. Oh, okay, I'm running out of time. So this is the slide that is important to me and I need to highlight. So Dipole Sonic is a good source of information. I highlighted how to get the idea about the minimum and maximum horizontal stress based on the polarization behavior of the Dipole Sonic. So, but the Dipole Sonic can travel based on the frequency, it can travel into different depths. So low frequency travels deep and probing deep to the formation, and a high frequency probing to the shallow interval. And as I mentioned, so Dipole Sonic can get polarized. So based on the different type of anisotropy, intrinsic anisotropy, bedding, and if there is a fracture, or induce stress induce. And this is the type of anisotropy that we are interested. And they did so many experiments, and they understood that whenever there is a stress anisotropy, fast and slow shear, they are traveling in the fast shear, traveling in the direction of the maximum horizontal stress in far field, and minimum horizontal stress, and slow shear is traveling in the direction of the minimum horizontal stress in the far field. But what is happening around the borehole is completely different. So around the borehole, the maximum stress concentration is happening in the direction of the minimum horizontal stress, right? So then you should expect some sort of crossing happening between the fast and the slow shear. And then they did lots of back calculation, and there is another plot. This is the frequency with frequency versus slowness versus frequency. But there is another plot which is showing slowness versus depth, which is radial profiling plot. And they are back calculating amount of horizontal stresses, and basically by changing into the Farfield stress, this pattern, this shape is still going to see a crossing, but the shape is going to be different. So they are going to be more apart from each other. So this is the technique that Schlumberger is using, and I have a SB paper so that you can read and learn more about this technique. But based on this technique, they are back calculating the minimum and maximum horizontal stress. But there are some limitation into this technique, not limitation, but there are some difficulties to implement this technique. There is it is not easy to sense. So I love the physics. I love the mathematics behind it. It is very complex and it's well established. I was promoting this technique and still promoting, still fan of this technique. But it's not easy to sense. It needs lots of education. And so the thing that you are converting sonic data to stress data, this translation is not easy to understand for some people. But it is, as I said, this is a well-established workflow. The thing that I'm currently busy, and I found that it could be a very good source of understanding the stress and isotropy and characterizing the formation, is using an instrumented packer. Basically what we are doing, so this is what I'm busy currently through the finite element modeling and RS2 and FLAG 2D. This is what I'm doing. So basically, what we are doing is inflating a packer, and the packer has some caliper readings. And by having the caliper readings, so we are back calculating the amount of horizontal stresses and elastic and rock strength property. This is the packer. And this is on RS2. I am following, because RS2 has its own limitation, FLAG 2 has another limitation. So I have to combine these two solutions to come up with the best answer. But the workflow is like this, that if you imagine that there is a point here, there is a cell here, a node here of the finite element model. If you can measure the, if you can, based on the modeling, you come up with the horizontal displacement, for example, and then you compare it with the caliper measurement. So these are the caliper measurement. If you are seeing a good match between the observation and the model, you can say that your model is functional and it's working. And then the other parameters that you are using into your model, they are accurate and they are representative of your formation. Okay. This is intelligent packer, so it's instrumented packer. So I have another 2 slides. I go through them quickly. I know that we are running out of time, but this is important. Stresses, they are not fixed. So you calculate them. So because the field is going through the production or injection, for example, EOR or CCS, carbon capture storage, or through this production or injection, so the stresses in your field can change. And you need to understand, you need to be able to calculate those changes. So you can use the 1D workflow. For example, these are the equations that around the kappa, and by knowing the maximum horizontal stress and minimum horizontal stress and amount of depletion, you can calculate that how much could be the minimum and maximum horizontal stress, depletion, reduction or increase, right? And this is, for example, one scenario that depletion in that particular zone was causing that we are missing the safe mode window, and we are not able to penetrate deep to the reservoir. This can happen if there is, for instance, depletion in this interval that happened in this case. So there are other consequences into stress changes, such as fault reactivation, subsidence, compaction, casing collapse. This is the fault reactivation modeling workflow. And we need to characterize this behavior. So we can use 1D approach, as I explained, but the best approach going to utilizing 3D and finite element and numerical modeling. So because you can include complex stratigraphy, complex geology, and even you can incorporate into your model faults, fractures, DFN, discrete fracture network, and this sort of information. And you can use the finite element codes to come up with the big picture and more representative stress state. And then, for example, in this scenario, if there is a depletion in this zone and a stress change in this zone, we know that the stress change is not going to stay purely in this interval. It's going to project itself into the adjacent layers, but 1D workflow has its own limitation and it cannot solve for this problem. This is the last slide, I promise. So you need to validate your model. You need to make sure that your model is working. You need to put it into try. And here is one of the typical screening of the drilling activities, which are giving some indication about the geomechanical model and what is happening in your well, for example. So you can see tight hole, we have a screen tight hole, rim interval, and there is a stock pipe here. They are all indicating that something happening in these intervals at these depths, and there should be a relation to geomechanical behavior and characters of your formation. So you can use caliper data if there is an enlargement, if there is a breakout based on the borehole caliper or image log. You can use this source of information to, calibrate your model. I go to laser point. For example, here, what is happening, this is a safe mod window, and then the mod weight is lower than the breakout. And this is a synthetic image log. We were predicting that in these intervals, there could be a breakout, and this is the actual caliper. So I know that this is not the perfect match, or the model was not able to predict well and work well in this interval. But for example, in this particular interval, the model was able to predict very advanced shear failure, which is the high angle echelon. So, and it was obvious on the caliper. It is showing the caliper is showing that there was even not enlargement, so opposite. So there was a reduction into the caliper measurement. And then if there is a fault reactivation, earthquake, macroseismicity, casing collapse, caprock failure, surface subsidence, sand production. So these are all the information that your model should be able to predict, should be able to reproduce, to make sure that your model is accurate and representative well for the other application, for example. And thank you very much. Sorry, I know that it took longer than I was anticipated, but hopefully I managed to pass the message. And these are my contacts. So you can reach out to me through any of these email address or my phone number. So I'm more than happy to be able to answer your questions or be helpful. Thank you, Serhi. Sorry.
Yeah, thank you for the presentation. It was very interesting. So please unmute yourself if you have any questions or write down it in the chat.
Sorry, I could go one. Yeah.
Is there any? Okay, I'll start then. So how do you characterize your mechanical earth model if you have a lot of local stress disturbance in the reservoir? Is it just probabilistic you are doing it, or how do you deal with that?
Oh, you mean that if there is a complex formation, for example?
Mm-hmm.
So personally, I prefer if there is a lots of complexity in your field. So I prefer to go 3D geomechanical modeling because they are more advanced, they are more robust, and for sure you have to start with the 1D. So you start with the 1D and then propagate it to 3D, and by incorporating horizons, and so the utilizing the seismic data, because these are not able to be incorporated into 1D model. So my workflow is using the 1D mechanical earth model as the pillars of the 3D model. But using the finite element code is what I prefer for that complicated scenarios to be utilized. And the good thing is that currently, so it is not like, for example, even 5 years ago. So accessing to the high CPU power, so cloud computing and cloud processors, it's very accessible at this moment. So you don't need a big machine. You can run it even, so you can see it even on your Chromebook and run simulations on the cloud, right? So you don't need the fancy machine. It is very accessible and very promising to be able to run advanced workflows on the simple and normal machines that they are not. It was not the case a few years ago.
Yeah, thank you. How do you measure Biot coefficient?
Okay, so you can calculate the Biot coefficient. There is a relation between the bulk modulus of the rock and the bulk modulus of grain. So measuring the bulk modulus of the formation is easy, but the grain, you have to define the mechanical stratigraphy. And then if you have access to lab to calculate the grains, because we are talking about the grains, not the whole bulk rock. So you can back calculate, there is a formula, so to calculate the Biot coefficient. Yeah, you can calculate it basically.
Got it. There is a question in the chat. Sure. Thanks for your presentation. How do you consider the fracture in your geomechanics model?
Oh, this is good. So to consider fractures into the 1D MEM, so basically it is very, unless you want to understand that the fracture slippage or this sort of simple workflows, so you can do it in the 1D or simple more column approach. But the best way to incorporate faults and fractures is going to be 3D geomechanical modeling. So you can even have the network of the fractures, DFN, so into the workflow that, for example, defined in the Petrel, Visage solutions. Yeah.
I do have a question.
Sure.
Yeah. So when you look at a sonic log, for example, if they're not doing any like an isotropy reading, it's just like one value of Young's modulus that they're interpreted. Is that like a vertical, like, so I do like mechanical testing. So is that sonic log for kind of like the horizontal Young's modulus or the vertical Young's modulus? Does that make sense? Kind of like if you, okay.
Oh, you're talking about the intrinsic and isotropy, right? So if there is a lamination.
Yeah. So like usually sometimes sonic logs only provide you like one Young's modulus interpreted, right? Like if you get like a log, is that like as if you were testing the rock perpendicular to the bedding, or is it parallel to bedding? That's my question.
Okay, so if I understood correctly, so you're talking about the intrinsic and isotropy and how can we use the sonic measurements to use, there are different techniques. So if you heard about the any, many, and also what is established around the sonic scanner measurements. So have you explored those? So because there are basically some sort of simplification into the problem. So to come up with the anisotropic properties based on the sonic and other measurements. So if you search for the any and many approaches, so it can be a good starting point to understand better how to utilize this information for that purpose. And even if you couldn't find it, so just drop me an email. I can share a literature which is related to this topic.
Okay,
Is it
thank
good?
you.
You're
Yeah,
most
well,
welcome.
my question was a bit more like they didn't provide us with, like, for example, if they only provide one Young's modulus, for example, does that means like it's only like the vertical Young's modulus? I don't know whether that makes sense, because technically if we're considering an isotropy, there should be like Young's modulus in the vertical direction and the horizontal direction.
Yeah,
No?
so based on the tool measurements, so it's going to be the, based on my knowledge, it's going to be the vertical one. And if you want the horizontal one, so that just only one measurement is going to be the vertical one. Yes.
Okay, thank you.
You're most welcome.
Okay, are there any more questions?
Yes, I have one question.
Sure.
I thank you for the presentation.
You're most welcome.
So I don't know if you are familiar with the fiber optics, distributed strength sensing and distributed acoustic sensing. And today we were talking about hoop stresses, right? The Kirsch equations and all of that. So I would like to know if you have some knowledge or background on these, like what is the difference when you get like the data from fiber, you see that field of strain, that is basically there is a mixture there. Strain because of the well bore effects and also because of the fracture propagation. So I would like to know if you have some insights about how impactful is the strain coming from the Kirsch equations, the hoop stresses and all of that compared to the fracture propagation in such type of data.
To be honest, I never got to the application of this fiber optics and these things. So it is kind of new. I heard something, but I was not involved. If you don't mind, if you drop me an email, so I can dig more to if I can find something. But no, I was not involved into this sort of projects, unfortunately.
No worries. Thank you very much.
I'm so sorry.
No worries.
It was not helpful.
Because like
looks advanced to me.
Yeah, because like when you go to the field and you get the data coming from fiber, okay, that's strain or temperature, but I'm more focused right now on strain. And people just say, oh, that's the fracture propagation. But like there is an effect coming from the well bore. That is coming from the Kirsch equations due to like when we have a well bore, we have strain around that well bore, right?
Yes.
So just because of the well bore, so there is an element in the fiber data that is actually related to the well bore. So, but that's okay. I'll try to send you.
No, I understand. It is pretty much same as getting information about the displacement of the borehole wall.
That's correct.
And yeah, this is, I can say it is pretty much, so I can see the relation.
That's
so
right.
It's pretty much same as what I'm exploring here.
Yes.
So we have those caliper type of sensors to measure physical measurement. And but what you are saying, if I understood correctly, using the fiber data to grab this information, which is very valid. So you can come up with the solution. So by having the fiber, you cannot inflate the borehole and deflate, loading, unloading, but you can get a sense about the borehole deformation and correlate it to the Farfield stresses. Yes, that's a good idea.
That's what I'm asking. And like, actually I'm modeling these stuff, but I'm about to get to put the Kirsch equations right now.
So I personally recommend that, because the Kirsch equation, so you cannot understand the borehole deformation. So it's missing that component. So you have to use finite element code.
Okay.
So you check on the RS2 from Rock Science or Black 2D. So your solution is plane strain. So you don't need complex 3D solution. So just one plane, and then just drop me an email. I'm interested to this topic.
Okay.
Thank you.
Thank you very much. Thank you.
If I pronounce your name correctly,
you can call George.
George. Okay, George is easier. Thank you, George.
Thank you.
Cheers.
Okay, thank you very much. Are there any last questions? If not, I would like.
Go ahead, please. I guess there is no question, right? So
if there are no questions,
I leave it to Serhi that close
Thank
the call,
you very
please.
much for your presentation, Mr. Heidari. It was very informative and interesting for the audience. Yes. So, and thanks everyone for joining it.
Thank you, everyone.
Friday.
Thank you, Serhi, again, and have a wonderful day.
A wonderful evening.
Looking forward to being more in contact with you guys. Cheers.
Thank you.
Bye-bye.
Bye-bye.